You think you're sitting on something solid right now. You're not. You're floating through mostly empty space, held up by invisible forces between atoms that are themselves 99.99% empty. And that's just the beginning of how deceived you've been about the nature of reality. Here's what's going to break your brain today. If you took all the actual stuff, all the matter in every human being on Earth, and removed the empty space, the entire human population would fit into a volume smaller than a sugar cube. 7 billion people, one sugar cube. And we're not even talking about the emptiness of space itself yet. Right now, as you watch this, you're hurtling through the most desolate, vacant, impossibly sparse structure imaginable. The universe isn't mostly empty. It's almost entirely empty. And the word almost is doing heavy lifting there that would make a bodybuilder jealous. By the end of this video, you're going to understand why everything you've ever touched, every solid surface you've ever walked on, every wall you've ever leaned against, none of it was ever really there. Not in the way you think. But before we dive into this rabbit hole that goes deeper than you can possibly imagine right now, I need you to do something. Hit that like button. Smash that subscribe button. Because what you're about to learn will fundamentally change how you see reality. And you're going to want to remember where you heard it first. Also, drop a comment right now telling me what country you're watching from and what time it is where you are. I want to know how far across this mostly empty universe this message is traveling. Let's start with something you think you understand. Atoms. You've seen the diagrams. A nucleus in the center with electrons orbiting around it like a tiny solar system. Cute. Wrong, but cute. Here's the first mind-bending reality. If an atom were the size of a football stadium, the nucleus would be smaller than a marble sitting on the 50-yard line. The electrons? They'd be tiny specks orbiting somewhere in the outer parking lots. Everything in between? Absolutely nothing. Pure, unadulterated void. Ernest Rutherford discovered this in 1911 with his famous gold foil experiment, and it shook the scientific world. He fired alpha particles at a thin sheet of gold, expecting them to pass through with maybe slight deflections. Most did, but some bounced straight back, which should have been impossible if atoms were solid. Rutherford himself said it was like firing artillery shells at tissue paper and having them bounce back at you. The only explanation? Atoms are mostly empty space with a tiny, dense nucleus. Think of it like this. Imagine you're standing in the middle of the Sahara Desert. The nearest other person is 1,000 miles away. That's still more dense than the inside of an atom. An atom is lowlier than the loneliest place you can imagine. But here's where it gets weird. You can't actually fall through your chair, even though both you and the chair are mostly empty space. Why? It's not because there's actual stuff there. It's because of something called the electromagnetic force electrons repelling other electrons. You're not sitting on your chair. You're hovering nanometers above it, held up by the mutual repulsion of electron clouds. You've never actually touched anything in your entire life. You've never touched another person. You've never touched your phone. You've never touched food before eating it. Every kiss you've ever had, you didn't touch. There was always a gap, microscopic but absolutely real, kept open by electromagnetic forces. Your lips got close enough that the electron clouds interacted, but they never made contact. True physical contact, at the atomic level, is impossible. The Danish physicist Niels Bohr refined our understanding of atomic structure in 1913, showing that electrons don't actually orbit like planets, but exist in probability clouds regions where they're likely to be found. But even these clouds are mostly empty. An electron is so small that if you scaled it up to the size of a marble, a hydrogen atom would be several miles across. Now, before you think, okay, but at least the nucleus is solid, let me destroy that hope too. The nucleus itself, made of protons and neutrons, is also mostly empty space. Protons and neutrons are made of quarks, held together by gluons, and the space between quarks, You guessed it. More emptiness. Here's a thought experiment. Take your hand. Look at it. It seems solid, right? It's made of approximately 7 octillion atoms. That's 7 followed by 27 zeros. If you could remove all the empty space from those atoms, really pack them together without any gaps, your hand would be smaller than a grain of sand. And it would weigh exactly the same. The matter that makes up your entire body, compressed to eliminate empty space, would be invisible to the naked eye. All of you, every memory you've ever made, every thought you've ever had, every feeling you've ever felt contained in a speck smaller than the period at the end of this sentence. Okay, so atoms are mostly empty. Surely when we zoom out, things get more substantial, right? Wrong. So catastrophically wrong that it's almost funny. Let's talk about our solar system. You've seen the model's neat little spheres representing planets, all lined up in a row, maybe a few feet apart. Those models are lying to you. They're lying so hard that they should be arrested for fraud. If the sun were the size of a basketball sitting in the center of a football field, Mercury would be a pinhead about 15 yards away. Earth? A slightly larger pinhead about 40 yards away. Jupiter would be a ping-pong ball at the opposite end zone. And Neptune? Neptune would be 3 football fields away, and it would be smaller than a marble. But here's the thing that should blow your mind. That's not even considering the space beyond Neptune. The solar system doesn't end at Neptune. The Kuiper belt extends to about 50 astronomical units. Astronomical units, where one owes the distance from Earth to the Sun. The Oort cloud, the outer boundary of our solar system, extends anywhere from 5,000 to 100,000 astronomical units from the Sun. Let me put that in perspective with our football field model. If the Sun is still our basketball on the 50-yard line, the Oort cloud would extend for approximately 1,000 miles in every direction. 1,000 miles of almost nothing. Gerard Kuiper predicted the Kuiper belt in 1951, but we didn't confirm its existence until the 1990s. Why? Because there's so much empty space that we had trouble finding anything in it. The Oort cloud, hypothesized by Jan Oort in 1950, has never been directly observed. We only know it's there because of the comets that occasionally fall inward from that region. Imagine that we have strong evidence for a cloud of objects surrounding our solar system, but we've never seen it because it's so far away and so sparse that it's essentially invisible. Think of it like this. If you took all the mass in our solar system, the Sun, all the planets, all the moons, all the asteroids, all the comets, all the dust, everything, and spread it out evenly, the solar system would have a density so low that you'd call it a vacuum. In fact, the best vacuum we can create in laboratories on Earth is still denser than most of interplanetary space. Here's something that'll mess with you. The Sun contains 99.86% of all the mass in the solar system. Everything else, Jupiter, Earth, Mars, all the planets, moons, asteroids, comets, dust, all of it combined is just 0.14%. And even that tiny fraction is scattered across billions of cubic miles of empty space. When the Voyager 1 spacecraft left our solar system in 2012, it didn't cross some clear boundary. It gradually detected changes in the particles around it. It went from an incredibly sparse environment to a slightly less incredibly sparse environment. That's the difference between being in our solar system and being in interstellar space. One near perfect vacuum versus another near perfect vacuum that's slightly different in composition. The average distance between the Sun and Earth is 93 million miles. That's 8 light minutes away. When you look at the Sun, you're seeing it as it was 8 minutes ago, because that's how long light takes to cross that vast emptiness. Light, the fastest thing in the universe, traveling at 186,000 miles per second, still takes 8 minutes to cross the void between the Sun and Earth. Now here's where I want you to pause and really think about something. You are sitting on a rock, flying through space at 67,000 miles per hour. You're orbiting a gigantic nuclear furnace 93 million miles away. And between you and that furnace? Mostly nothing. If the Earth were a car driving on a highway, there wouldn't be another car within 1,000 miles in any direction. That's how empty our local neighborhood is. If you thought the solar system was empty, buckle up. We're about to zoom out, and things are going to get so sparse that your brain might actually struggle to process it. The nearest star to our sun is Proxima Centauri, about 4.24 light years away. That's 25 trillion miles. 25 million miles. In our football field model, if the sun is a basketball at midfield, Proxima Centauri would be another basketball in Atlanta, assuming you're starting in New York. Let that sink in. The nearest star to us, our closest stellar neighbor, is so far away that if you started walking toward it at 3 miles per hour, never stopping, never sleeping, it would take you 950 million years to get there. The space between stars is so empty that it makes the inside of atoms look crowded. Interstellar space contains, on average, about 1 atom per cubic centimeter. That might not sound too bad until you realize that the air you're breathing right now contains about 1,019 molecules per cubic centimeter. That's 10 billion molecules. Interstellar space has 1 atom per cubic centimeter. Think of it like this. Imagine you're standing in a completely empty warehouse the size of a city block. There's 1 single grain of sand somewhere in that warehouse. That's still 1,000,000 times denser than interstellar space. But wait, there's more emptiness. Between those atoms is something even more peculiar. Quantum fields permeate all of space, and these fields are fluctuating constantly, creating virtual particles that pop into and out of existence. But even these quantum fluctuations don't fill the void. They just make the emptiness slightly more interesting. In 1977, NASA launched Voyager 1 with a golden record containing sounds and images from Earth, hoping that any alien civilization that found it would learn about us. That probe has been traveling for over 45 years, moving at about 38,000 miles per hour relative to the Sun. It's now about 14.5 billion miles from Earth. And guess what? It hasn't even come close to another star. It won't reach the distance of Proxima Centauri for another 75,000 years. That's how vast the emptiness between stars really is. Here's something that should terrify and amaze you. If you somehow traveled to the space between stars and looked around, you would see stars in every direction, beautiful pinpoints of light scattered across the cosmic void. But if you picked any direction and started traveling, you could go for years, decades, centuries, potentially millions of years without hitting anything larger than a dust particle. The average density of the Milky Way galaxy is about 1 atom per cubic centimeter. But that's averaged out. Most of the space is far emptier than that, with occasional clouds of gas and dust that are slightly less empty. The densest molecular clouds in space, the ones where stars are born, have densities of maybe 1,000,000 particles per cubic centimeter. Sounds like a lot? It's still 10 trillion times less dense than the air you're breathing. Harlow Shapley, in 1918, measured the size of the Milky Way and humanity's position in it. He found that our galaxy is about 100,000 light years across. That's 587,863,200,000,000,000 miles. And within that incomprehensible expanse, there are an estimated 100 to 400 billion stars. Sounds crowded, right? Wrong. If you evenly distributed those stars across the volume of the galaxy, each star would have a personal space bubble hundreds of trillions of miles across. Here's a mind bender. Pick any random location in the Milky Way galaxy. The probability that there's anything at that location, anything at all, even a single atom, is so close to zero that it might as well be zero. The universe is so committed to being empty that if you randomly materialized anywhere in our galaxy, you would almost certainly appear in the middle of nothing, with the nearest atom potentially millions of miles away. Ready for this to get even more insane? Let's zoom out one more level. The Milky Way galaxy is part of the local group, which contains about 54 galaxies. The nearest major galaxy to us is Andromeda, which is 2.5 million light-years away. In our models so far, we've been using football fields and cities. For this scale, if the Milky Way were the size of a dinner plate, Andromeda would be another dinner plate about 20 feet away. That doesn't sound too bad, right? Here's the thing. Those dinner plates are mostly empty space too. Remember, galaxies themselves are mostly void. So we have empty things separated by vast distances of even more emptiness. The space between galaxies' intergalactic space is the emptiest place in the universe. The average density? Roughly 1 hydrogen atom per cubic meter. That's 1 atom in a space about the size of a washing machine. And remember, that's average. Much of intergalactic space is far emptier than that. The air you're breathing has about YY molecules per cubic meter. Intergalactic space has 1 atom per cubic meter. That means the air around you is 10 trillion times denser than the space between galaxies. Here's something that'll make your head spin. The local group of galaxies occupies a region about 10 million light-years across. Beyond that, there's an even larger structure called the Virgo supercluster, which contains about 100 galaxy groups and clusters. And beyond that, the Laniakea supercluster, which contains about 100,000 galaxies across 520 million light-years. But here's the kicker. Between these superclusters are cosmic voids. These are regions of space with very few galaxies, spanning hundreds of millions of light-years across. They're called voids for a reason. They're not completely empty. There might be a few stray galaxies wandering around in there, but they're as close to absolute nothingness as the universe gets. The Boat's void, discovered in 1981 by Robert Kirshner and colleagues, is about 330 million light-years in diameter. It contains only about 60 galaxies. If it had the average density of the universe, it should contain about 2,000 galaxies. It's empty even by the standards of an already mind-bogglingly empty universe. Think of it like this. Imagine you're standing in the middle of the Pacific Ocean. No land in sight. That's lonely, right? Now imagine that ocean is 1,000 times larger, and instead of water, it's vacuum. And instead of being at sea level, you're floating in the middle of it, suspended in nothing. That's a cosmic void. Now imagine that void is not thousands of miles across, but hundreds of millions of light-years across. That's the scale we're talking about. Here's something that demonstrates just how empty the universe is. The entire observable universe contains about YY atoms. That sounds like a lot, and it is. But the observable universe is 93 billion light-years across. If you spread those atoms out evenly, you'd have about 1 atom per cubic meter. The entire universe, on average, has the density of intergalactic space. Let me put this another way. If you could shrink the observable universe down so that each galaxy was the size of a grain of sand, and you spread those grains of sand out proportionally, you'd have a sandbox about 200 feet across with about 200 billion grains of sand in it. Sounds dense? It's not. That's still mostly empty space with occasional grains of sand. In 1998, astronomers Saul Perlmutter, Ryan Schmidt, and Adam Rees made a discovery that would win them the Nobel Prize. The universe isn't just expanding, it's accelerating. Dark energy is pushing galaxies apart faster and faster. What does this mean for emptiness? It means the universe is getting emptier. Every second, the voids between galaxy clusters are growing. The universe is literally becoming more nothing as time goes on. All right, let's zoom all the way out. The observable universe is everything we can see, in principle, from Earth. It's limited by the age of the universe and the speed of light. Light from objects farther than about 46.5 billion light-years away hasn't had time to reach us yet, so we can't see them. The observable universe is a sphere centered on Earth, 93 billion light-years across. How much stuff is in this sphere? About YY atoms, give or take a few orders of magnitude. That's a 1 followed by 80 zeros. That seems like a lot, right? It's actually not that much, given the volume we're talking about. The volume of the observable universe is about 41,080 cubic meters. We have YY atoms. That's an average density of about 0.25 atoms per cubic meter, a quarter of an atom per cubic meter. The entire observable universe, averaged out, is emptier than intergalactic space. But here's what really should break your brain. The observable universe probably isn't the whole universe. It's just the part we can see. The actual universe might be infinite. And if it's infinite, that means there's an infinite amount of emptiness out there. Think about what that means. An infinite universe doesn't mean infinite galaxies packed infinitely close together. It means infinite space, with galaxies scattered throughout it at roughly the same sparse density we observe locally. Infinity multiplied by almost nothing is still infinity of mostly nothing. Here's another thought experiment. Imagine you could travel at the speed of light in any direction from Earth. You'd pass the Moon in 1.3 seconds, the Sun in 8 minutes, Pluto in 5.5 hours, the nearest star in 4.24 years, the center of the Milky Way in 26,000 years, Andromeda in 2.5 million years. And if you kept going, you could travel for billions of years without ever leaving the mostly empty universe. The cosmic microwave background radiation, discovered by Arno Penzias and Robert Wilson in 1964, is the afterglow of the Big Bang. It comes from every direction in space, from the edge of the observable universe. When we study it, we can measure the density of the early universe. You know what we found? Even 380,000 years after the Big Bang, when the universe was much smaller and denser, it was still mostly empty space. The universe started from an incredibly dense, hot state and has been expanding and cooling ever since. But incredibly dense is relative. Even at the moment of the Big Bang, space itself was expanding faster than matter could fill it. Emptiness has been winning since the beginning. Let me give you a sense of scale that might help, or might make things worse. If you represented every atom in the observable universe as a grain of sand, and you spread them out proportionally, according to their actual distribution in space, you'd have a beach billions of light years across, with occasional grains of sand scattered so far apart that you'd never find two within 1,000,000 miles of each other. Now, if you're thinking, okay, but surely all this emptiness is filled with something dark matter, dark energy, something, you're partially right. Dark matter and dark energy do exist, and they do fill space. But here's the thing. They're called dark because they don't interact with light or normal matter except through gravity. They're essentially invisible, intangible, and pass right through everything without resistance. So yes, space is filled with dark matter and dark energy. But for all practical purposes, from the perspective of normal matter, it's still empty. Dark matter makes up about 27% of the universe's mass energy. Dark energy makes up about 68%. Normal matter, the stuff you're made of, the stuff stars are made of, the stuff everything you've ever seen is made of, makes up only 5% of the universe. And that 5% is mostly scattered across vast, empty space in the form of incredibly sparse hydrogen gas, with occasional dense clumps we call stars and planets. Here's where things get philosophically weird. We've established that the universe is almost entirely empty space. But is empty space actually empty? According to quantum field theory, the answer is no. Empty space, what physicists call the quantum vacuum, is seething with activity. Virtual particles are constantly popping into and out of existence. Quantum fields fluctuate. The vacuum has energy. Werner Heisenberg's uncertainty principle, formulated in 1927, tells us that you can't simultaneously know both the position and momentum of a particle with perfect precision. This has a weird consequence. Energy and time also have an uncertainty relationship. This means that for very short periods of time, energy can be borrowed from nothing, creating particle-antiparticle pairs that exist briefly before annihilating each other. These aren't hypothetical. We've detected their effects. The Casimir effect, predicted by Hendrik Casimir in 1948 and experimentally confirmed in 1997, shows that two metal plates placed very close together in a vacuum will be pushed together by quantum vacuum fluctuations. The vacuum between the plates has fewer possible quantum fluctuations than the vacuum outside, creating a pressure difference. Empty space literally pushes on things. So is space really empty? Depends on what you mean by empty. There's no matter there, but there's quantum fields, virtual particles, vacuum energy, and the fabric of space-time itself. But here's the thing. All of that still doesn't make space full in any meaningful sense. You still can't touch it, breathe it, or interact with it in normal ways. Think of it like this. Imagine a room that's empty except for Wi-Fi signals passing through it. Is the room empty? Physically, yes, you could walk through it without bumping into anything. But technically, it's filled with electromagnetic radiation. That's what the quantum vacuum is like. Except the signals are quantum fields that can occasionally manifest as temporary particles. Paul Dirac, in 1930, predicted the existence of antimatter based on his quantum equations. He proposed that the vacuum is actually a sea of negative energy particles, and what we perceive as particles are actually holes in this sea. His prediction was confirmed in 1932 with the discovery of the positron. This was revolutionary. The vacuum isn't nothing. It's a something that can be disturbed to create what we perceive as matter. But even this quantum foam, this seething vacuum of virtual particles and quantum fields, doesn't change the fundamental emptiness of space. The average energy density of the vacuum is incredibly small, about Y-9 joules per cubic meter. That's nearly nothing. You contain more energy in your body just by existing than a vacuum the size of a building contains in its quantum fluctuations. Here's something that'll really bend your mind. According to some interpretations of quantum mechanics, particles don't even have definite positions until they're measured. They exist as probability waves spread out over space. So in a sense, even the stuff that exists in the universe is somewhat non-local, fuzzy, spread out. Matter itself, at the quantum level, is less concrete and more ghost-like than you ever imagined. The Higgs field, confirmed in 2012 with the discovery of the Higgs boson at CERN, permeates all of space. It's what gives particles their mass. But again, this field doesn't make space full. It's just another quantum field joining all the other quantum fields that fill the universe. And even with all these fields present, space is still, for all practical purposes, empty. Let's talk about something even stranger, the emptiness within forces themselves. You know how we said earlier that you can't actually touch anything? Let's dig deeper into that. When you push on a wall, you feel resistance. But that resistance isn't coming from solid matter touching other solid matter. It's coming from the electromagnetic force, specifically. The repulsion between the electron clouds in your hand and the electron clouds in the wall. Forces, in modern physics, are mediated by particles. The electromagnetic force is carried by photons. The strong nuclear force is carried by gluons. The weak nuclear force is carried by W and Z bosons. Gravity is theorized to be carried by gravitons, though we haven't detected them yet. But here's the thing. These force carrier particles are constantly being exchanged between particles, and most of the time, they exist as virtual particles, quantum fluctuations that appear and disappear so quickly that they can never be directly observed. They're ghosts of particles, messenger spirits, carrying information between matter, flying through emptiness. When you lean against a wall, what's really happening is that the electrons in your atoms are getting close to the electrons in the wall's atoms. They start exchanging virtual photons, particles of light that exist for such a brief moment that they can violate the laws of physics, carrying momentum and force before vanishing. These virtual photons push the electrons apart, which you experience as the wall being solid. But the wall isn't solid. The electrons aren't solid. The force itself is being carried by particles that don't really exist in the traditional sense. You're being held up by quantum ghosts moving through emptiness to prevent other emptiness from colliding with your emptiness. Richard Feynman, one of the architects of quantum electrodynamics, developed a way to visualize these interactions in the 1940s with what we now call Feynman diagrams. These diagrams show particles exchanging virtual particles, and they reveal something profound. At the quantum level, forces are just particles, which are also waves, which are also probability distributions, exchanging other particles, which are also waves, which are also probability distributions, which might not even actually exist across empty space. The strong nuclear force, which holds quarks together inside protons and neutrons, is carried by gluons. But gluons have a weird property. They interact with each other. Photons don't interact with other photons, but gluons do. This means the force that holds the nucleus together is itself interacting with itself, creating a roiling, seething mess of force carriers creating and annihilating each other in the tiny space of the nucleus. But even there, in the densest place in ordinary matter, there's still emptiness between the quarks. Here's something that should blow your mind. The mass of a proton is about 938 MeV, million electron volts. But if you add up the masses of the 3 quarks inside it, you only get about 9 MeV. Where does the other 99% of the mass come from? It comes from the energy of the gluon fields binding the quarks together. E equals mc. The mass is the energy of the binding force divided by the speed of light squared. This means that 99% of your mass, 99% of the mass of everything you can touch isn't coming from matter at all. It's coming from the energy of force fields in the empty space inside nuclei. You're mostly made of empty space. And the stuff that gives you weight is mostly the energy of forces acting in that empty space. You're not even mostly made of matter. You're mostly made of trapped force energy pretending to be matter. Gravity is even weirder. Einstein showed in 1915 that gravity isn't a force being transmitted through space. It's the curvature of spacetime itself. Massive objects bend spacetime, and other objects follow that curvature. You're not being pulled down by Earth. You're following the straightest possible path through curved spacetime, and that path happens to lead you toward the ground. So even gravity, the force you feel constantly pulling you down right now, isn't a force in the traditional sense. It's geometry. It's the shape of empty space being distorted by mass. Empty space itself becomes curved, and you follow that curve. Let's bring this back to you. You personally, sitting there, watching this video. You are a temporary pattern of mostly empty atoms, held together by forces carried by virtual particles. Sitting on a mostly empty rock, flying through mostly empty space, orbiting a mostly empty solar system, in the outer reaches of a mostly empty galaxy, in a mostly empty universe that's getting emptier by the second. Every person you've ever loved is made of emptiness. Every place you've ever been exists in a vast sea of nothing. Every achievement of humanity, every building, every book, every piece of music, every work of art is a brief, sparse arrangement of atoms that are themselves almost entirely void, floating in an incomprehensibly empty cosmos. And yet, here you are, conscious, aware, thinking about your existence in this void. The fact that you exist at all is statistically absurd. The probability that the atoms that make up your body would arrange themselves in exactly this configuration, in exactly this place, at exactly this time, is so infinitesimally small that it might as well be zero. Think about this. The atoms in your body are billions of years old. They were forged in the hearts of stars that lived and died long before Earth existed. Those stars exploded in supernova, scattering their atoms across space. Those atoms drifted through the emptiness of interstellar space for millions of years. They eventually condensed into new clouds of gas and dust. Some of those clouds formed our solar system. Some of those atoms ended up on Earth. Some of those atoms ended up in the food your mother ate while she was pregnant with you. And now those atoms are you. You are made of star stuff, as Carl Sagan famously said. But more accurately, you're made of the rare, sparse star stuff that happened to collect together in a temporary arrangement in the midst of overwhelming emptiness. The fact that you're conscious makes it even more remarkable. Your brain contains about 86 billion neurons. Those neurons are connected by about 100 trillion synapses. Those connections, firing in precise patterns, create your thoughts, your memories, your sense of self. But those neurons are cells made of molecules, made of atoms, made of mostly empty space. Your consciousness, your very sense of you, is an emergent property of emptiness arranged in a specific way. When you think a thought, what's physically happening? Electrical signals are traveling between neurons, but those signals are just electrons moving through mostly empty space. Chemical neurotransmitters are crossing synapses, but those neurotransmitters are molecules made of mostly empty atoms. Your thoughts are patterns of emptiness, signaling to other patterns of emptiness across gaps of yet more emptiness. And here's something that might comfort you or terrify you. Because you're mostly empty space, you're constantly being passed through by neutrinos' ghostly particles that barely interact with matter. Right now, as you read this, trillions of neutrinos from the sun are passing through your body every second. They go through the Earth as if it weren't there. They go through you without slowing down. You are so empty that you're transparent to most of the universe. The cosmic perspective reveals something profound. In terms of matter, you're insignificant. The mass of your body is nothing compared to the mass of Earth. The mass of Earth is nothing compared to the sun. The mass of the sun is nothing compared to the galaxy. The mass of the galaxy is nothing compared to the observable universe. And most of that mass is empty space anyway. But in terms of complexity, you're extraordinary. The number of possible neural states your brain can be in is larger than the number of atoms in the observable universe. Your consciousness is the most complex thing we know of in the cosmos. You are a pattern of emptiness that's aware of itself, capable of contemplating the very emptiness it's made of. So what does all this emptiness mean? Are we insignificant specks in an uncaring void? Or is there something more profound going on? Let's start with the emptiness itself. Why is the universe so empty? Why isn't space packed full of matter? There are actually good reasons for this, and they have to do with the fundamental forces of nature. If the universe were much denser, gravity would have caused everything to collapse into black holes almost immediately. After the Big Bang, stars wouldn't have time to form, planets wouldn't exist, life couldn't develop. The fact that the universe is so empty is actually necessary for complexity to arise. The cosmological constant, the amount of dark energy in the universe, has a value that's remarkably close to the threshold between eternal expansion and eventual collapse. If it were slightly larger, the universe would expand so fast that galaxies couldn't form. If it were slightly smaller, the universe would have collapsed back on itself long ago. We exist in a universe that's empty enough to allow structure, but not so empty that structure never forms. This has led some physicists to propose the anthropic principle. We observe the universe to have the properties it has, because if it had different properties, we wouldn't exist to observe it. The universe is empty, because if it weren't this empty, we wouldn't be here to ask why it's so empty. But there's a deeper philosophical question. What is emptiness, really? Is it just the absence of things? Or is it something in itself? In Buddhist philosophy, there's a concept called anyat, or emptiness, which suggests that all phenomena are empty of inherent existence. They only exist in relation to other things. A chair is only a chair because we've arranged atoms in a chair-like pattern, and we've decided to call it a chair. The atoms don't care. The universe doesn't care. The chairness exists only in the relationships between parts and in our minds. Modern physics echoes this in a strange way. The ancient Greek philosopher Democritus, around 400 BCE, proposed that everything is made of atoms and void. He was remarkably close to the truth, though he imagined atoms as solid, indivisible particles. Now we know that even atoms are mostly void. It's void all the way down. And yet, somehow, from this void, complexity emerges. Consciousness emerges. Meaning emerges. Here's a thought experiment that might reframe everything. What if emptiness isn't the absence of something, but rather the canvas on which everything is painted? What if the void isn't negative space, but rather the necessary precondition for existence? If space were completely full of matter, nothing could move. There would be no change, no growth, no evolution, no life. Emptiness is what allows possibility. It's what allows movement, change, transformation. The void isn't a bug in the universe. It's a feature. Existentialist philosophers, like Jean-Paul Sartre, argued that existence precedes essence, that we're thrown into existence in a universe without inherent meaning, and we must create our own meaning. The emptiness of the universe, from this perspective, isn't nihilistic. It's liberating. We're not constrained by a pre-existing cosmic purpose. We are free to define ourselves. And here's something beautiful. Despite all this emptiness, we connect. You reach out to touch someone you love, and even though you never truly touch them at the atomic level, something real happens. Information is exchanged. Emotions are communicated. Meaning is created. The fact that we're all mostly empty space doesn't diminish the reality of human connection. If anything, it makes it more miraculous. We've talked a lot about the emptiness of space, but what about the emptiness of time? Time is another dimension where emptiness plays a crucial role, though we rarely think about it this way. The universe is about 13.8 billion years old. That's a long time by human standards, but compared to infinity, it's nothing. The universe hasn't existed for most of eternity. There was no time before the Big Bang, or if there was, we can't access information about it. The universe emerged from nothing, in a very literal sense. But even within the history of the universe, most of time has been empty of life, consciousness, or complexity. For the first 380,000 years after the Big Bang, the universe was too hot for atoms to form. It was a soup of plasma electrons and nuclei bouncing around, unable to bind together. No stars, no planets, no chemistry, no life. Just emptiness being empty in a different way. The first stars formed about 100 million years after the Big Bang. That means the universe was empty of stars for its first 100 million years. Empty of starlight. Empty of the complex chemistry that only happens in stellar cores. Earth formed about 4.5 billion years ago. Life on Earth emerged around 3.8 billion years ago. But complex life multicellular organisms didn't appear until about 600 million years ago. Humans? We've only been around for about 300,000 years. Modern civilization? About 10,000 years. The Industrial Revolution? 250 years ago. The Internet? 35 years old. From the perspective of cosmic time, nearly all of the universe's history has been devoid of anything that could observe it, think about it, or care about it. The universe spent billions of years being empty in space and empty of consciousness in time. And here's the kicker. The future is even more empty. Due to dark energy and the accelerating expansion of the universe, galaxies are moving apart faster and faster. In about 100 billion years, every galaxy outside our local group will have moved beyond the cosmic horizon. They'll be receding faster than the speed of light, making them forever unreachable and invisible. In 1 trillion years, all the stars will have burned out. The universe will be dark. In 10,100 years, a googol years, even black holes will have evaporated due to Hawking radiation. The universe will consist of nothing but photons and other particles drifting apart in an ever-expanding void, getting colder and colder, approaching absolute zero. This is called the heat death of the universe. Not a dramatic collapse, but a slow, eternal fade-out into maximum entropy and minimum energy. The universe will become as empty as it's possible to be. No stars, no planets, no atoms, no structure, just a thin gruel of particles spread across infinite space at infinitesimal density, approaching absolute stillness. From this perspective, we live in a special time. We exist during a brief window, cosmologically speaking, when the universe is old enough to have stars and planets and life, but young enough that stars are still burning and galaxies haven't all drifted apart. We exist in a temporary island of complexity, in an ocean of emptiness that extends infinitely in both space and time. The physicist John Wheeler proposed the participatory anthropic principle, suggesting that consciousness and observation might play a fundamental role in bringing the universe into existence. In quantum mechanics, measurements collapse wave functions, turning probability into actuality. Does this mean the universe needs observers to be real? It's a controversial idea, but it raises a profound question. Is the emptiness of the universe real if no one is there to measure it? Let's talk about something that might seem unrelated, but is actually crucial to understanding. Emptiness, entropy, and information. Entropy is often described as disorder, but a better definition is that it's the number of ways a system can be arranged while looking the same at a macro level. A gas has high entropy because the molecules can be arranged in countless different ways while still being a gas. A crystal has low entropy because the molecules are arranged in a very specific ordered pattern. Now here's where it gets interesting. The entropy of a region of space is proportional to its surface area, not its volume. This is what the physicist Jacob Bekenstein discovered when studying black holes in the 1970s. Stephen Hawking expanded on this, showing that black holes have entropy proportional to the area of their event horizon. This led to the holographic principle, proposed by Gerard T. Hooft and Leonard Susskind in the 1990s. It suggests that all the information in a volume of space can be encoded on its boundary. In other words, reality might be a hologram, a three-dimensional projection of information encoded on a two-dimensional surface. If this is true, then the emptiness of space might be even more profound than we thought. The three-dimensional void might be an illusion. The real information might exist on a distant boundary, and everything we experience as three-dimensional space might be a projection. But even if space is a hologram, the principle remains. Most of the hologram is empty. Most of the information is zero. Most of reality, even if it's a projection, is blank canvas. Information itself has a physical cost. According to Landauer's principle, formulated by Rolf Landauer in 1961, erasing one bit of information requires a minimum amount of energy and generates heat. This connects information directly to thermodynamics and entropy. Information is physical, and the universe, being mostly empty, is mostly devoid of information. Think about what this means. When you store information, whether in your brain, on a computer, in a book, you're creating pockets of low entropy, ordered structure in the midst of emptiness. Every thought you have, every memory you store, is a rebellion against the universe's tendency toward maximum entropy and emptiness. But entropy always wins in the long run. The second law of thermodynamics is inexorable. Entropy always increases in a closed system. The universe is a closed system. Eventually, all structure will decay. All information will be lost. All order will dissolve into maximum entropy, which is another way of saying maximum emptiness. Life itself is an entropy-reducing phenomenon. Living things take low entropy energy, like sunlight or food, and use it to build complex, ordered structures like cells, organs, bodies, ecosystems. But this is only possible because we're not closed systems. We're constantly taking in energy from outside and dumping waste heat back out. We're local decreases in entropy, maintained by increasing entropy elsewhere. And here's something profound. Consciousness might be the universe's way of observing itself, of turning potential into actual, of collapsing quantum wave functions, of creating information from possibility. In a universe that's mostly empty and trending toward more emptiness, consciousness is a remarkable phenomenon, a pattern in the void that's aware of the void, that can think about the void, they can create meaning in the midst of meaninglessness. The physicist Max Tegmark has proposed that mathematical structures are real and that our universe is a mathematical object. If this is true, then the emptiness of the universe isn't just physical, it's mathematical. Most possible mathematical structures are empty. Most possible equations have trivial solutions. Most possible universes would be void. We've talked about the emptiness of normal matter, but we haven't fully addressed the elephant in the room, or rather, the invisible, intangible, undetectable elements that make up most of the universe. Dark matter makes up about 27% of the universe's mass energy content. We know it exists because we can see its gravitational effects. Galaxies rotate too fast to be held together by their visible matter alone. Galaxy clusters have more gravitational pull than their visible matter can account for. Gravitational lensing, the bending of light by gravity, reveals invisible mass. But we can't see dark matter. We can't touch it. We can't detect it directly with any instrument we've built. It doesn't emit, absorb, or reflect light. It doesn't interact with the electromagnetic force at all. It only interacts through gravity and possibly the weak nuclear force. So what is it? We don't know. It might be exotic particles that we haven't discovered yet, WIMPs, weakly interacting massive particles, axions, or something else entirely. We've built massive, sensitive detectors deep underground, shielded from cosmic rays, trying to catch dark matter particles as they pass through. So far, nothing. Here's the thing that should blow your mind. Dark matter is everywhere. It's passing through you right now. The Earth is moving through a cloud of dark matter. The Milky Way has a halo of dark matter surrounding it. But it's so weakly interacting that it passes through normal matter like we're not even there. From the perspective of dark matter, the universe is even more empty than from our perspective. Dark matter doesn't feel the electromagnetic force, so it doesn't bounce off things. It doesn't form atoms or molecules, or stars or planets. It just clumps under gravity, forming vast, diffuse halos around galaxies. To dark matter, we don't exist. We're the ghosts. We're the imperceptible wisps. But dark matter is downright crowded compared to dark energy. Dark energy makes up about 68% of the universe's mass energy content. And we know even less about it than we know about dark matter. What we do know is this: the expansion of the universe is accelerating. Galaxies are moving apart faster and faster. Something is pushing them apart. We call that something dark energy, but that's just a placeholder name. We have no idea what it actually is. The simplest explanation is that dark energy is the energy of empty space itself, the vacuum energy we talked about earlier. Einstein's equations include a cosmological constant term, which can be interpreted as the energy density of the vacuum. If this constant is positive, it causes space to expand. But here's the problem. When we calculate what the vacuum energy should be based on quantum field theory, we get a number that's 10,120 times larger than what we observe. That's not a typo. 120 orders of magnitude. It's the worst prediction in the history of physics. Something is canceling out almost all of the vacuum energy, leaving just a tiny residual amount. We don't know what or why. It's one of the biggest unsolved problems in physics. But from the perspective of emptiness, dark energy is crucial. It's literally making the universe more empty. It's pushing galaxies apart, expanding the voids between them, ensuring that the universe becomes increasingly sparse over time. In a sense, dark energy is the ultimate expression of cosmic emptiness. It's not just the absence of something. It's an active force making things more absent. It's anti-gravity, anti-clustering, anti-structure. It's the universe's way of ensuring that emptiness wins in the end. Some physicists speculate that dark energy might change over time. Maybe it will strengthen, causing a big rip where the expansion accelerates so much that atoms themselves are torn apart. Maybe it will weaken, allowing gravity to eventually halt expansion and cause a big crunch where everything collapses back together. Maybe it will stay constant, leading to the heat death we discussed earlier. We don't know. But what we do know is that the universe's fate is controlled by something we can't see, can't detect directly, and don't understand. The invisible emptiness is in control. Let's flip the script for a moment. What if we've been thinking about emptiness wrong this entire time? From one perspective, the universe is almost entirely empty. But from another perspective, the universe is completely full of fields, full of potential, full of possibility. Quantum field theory says that every point in space is filled with fields. The electromagnetic field exists everywhere. The Higgs field exists everywhere. The graviton field, if it exists everywhere. Space isn't empty, it's a plenum, a fullness of overlapping fields. Particles, in this view, aren't little billiard balls. They're excitations in these fields. An electron isn't a thing that exists in space. It's the electron field being excited at a particular location. A photon isn't a particle of light traveling through space. It's a traveling wave in the electromagnetic field. From this perspective, there's no such thing as empty space. There's only field space, and fields are everywhere. What we call emptiness is just the ground state of all these fields, the state they're in when they're not excited into particles. But even the ground state isn't truly empty. It's bubbling with vacuum fluctuations, virtual particles, zero-point energy. The Casimir effect and the Lamb shift are experimental confirmations that the vacuum is real and has physical effects. Some interpretations of quantum mechanics go even further. The many worlds interpretation, proposed by Hugh Everett in 1957, suggests that every quantum measurement causes the universe to split into multiple branches, one for each possible outcome. If this is true, then the apparently empty space around us is actually filled with countless parallel universes, each slightly different, existing in the same space, but in different quantum branches. From this view, what looks empty is actually infinitely fulfilled with every possibility simultaneously existing in separate branches of reality. You're not sitting in an empty room. You're sitting in a room that's simultaneously filled with infinite versions of yourself and your surroundings, each in a slightly different state, all existing in superposition until observation collapses them into one experienced reality. This is speculative, of course. We don't know if the many worlds interpretation is correct, but it illustrates an important point. Emptiness is relative to your frame of reference and your level of analysis. There's also the informational perspective. Some physicists, like John Wheeler, propose that information is fundamental to reality. It from bit, as he put it. In this view, the universe is made of information, and what we call matter and energy are just ways information manifests. From an informational perspective, empty space isn't empty. It's filled with information about the state of all fields at every point. Most of that information happens to be zero or ground state, but it's still information. The emptiness itself carries information. Claude Shannon, the father of information theory, showed in 1948 that information can be quantified and that there are fundamental limits to how much information can be stored and transmitted. If the universe is made of information, then there's a maximum information density possible, which might explain why the universe can't be packed full of matter. String theory offers yet another perspective. In string theory, what we think of as particles are actually tiny vibrating strings of energy. Different vibration patterns create different particles. But these strings exist in more than the 3 spatial dimensions we experience. They exist in 10 or 11 dimensions, most of which are compactified, curled up so small that we can't perceive them. If string theory is correct, then what looks like empty 3-dimensional space is actually filled with these extra dimensions. You're not in an empty room. You're in a room filled with 6 or 7 extra dimensions, curled up at every point, each smaller than an atom. The emptiness of our three-dimensional space masks the fullness of higher dimensional space. Here's a thought that might change everything we've discussed. What if the universe is a simulation? The simulation hypothesis, popularized by philosopher Nick Bostrom in 2003, suggests that if civilizations can create realistic simulations of conscious beings, and if such civilizations are common, then statistically we're more likely to be in a simulation than in base reality. If the universe is a simulation, then the emptiness makes perfect computational sense. Why would you render every atom, every particle, every quantum fluctuation in every cubic meter of space if no one is observing it? That would be computationally wasteful. A smart simulation would only render what's being observed, leaving the rest in a minimal state. And what's the minimal state? Emptiness. The vast majority of the universe is empty because it doesn't need to be simulated in detail. It's like the unrendered parts of a video game. They exist as abstract data structures, not as fully realized visual representations. The quantum measurement problem fits eerily well with this idea. Quantum systems exist in superposition until measured, at which point the wave function collapses into a definite state. In simulation terms, the system exists as a probability distribution, computationally cheap to store, until it's observed, at which point it's rendered into a specific state, computationally expensive but necessary. The speed of light could be understood as a frame rate. Limit information can only propagate through the simulation at a maximum speed. The Planck length, 1035 meters, could be the pixel size, the smallest meaningful unit of space. The Planck time, y-43 seconds, could be the tick rate, the refresh rate of the simulation. If this is true, then the emptiness of the universe isn't a bug, it's optimization. The simulation is maximally efficient, only computing what needs to be computed, leaving everything else in a default empty state. But here's the thing. Even if we're in a simulation, the experience of emptiness is real. The loneliness of the cosmos, the vast voids between galaxies, the sparse distribution of matter, these are real features of our experienced reality, whether that reality is fundamental or simulated. And if we're in a simulation, what about the reality running the simulation? Is it also mostly empty? Or is it packed full of matter and energy? We have no way of knowing. We're trapped inside our simulation, if it is one, with no way to see outside. Some physicists have looked for glitches in reality that might indicate we're in a simulation. They've examined the cosmic microwave background for patterns that might suggest pixelation or processing artifacts. So far, nothing conclusive. But the search continues. The philosopher René Descartes, in the 17th century, asked how we can know anything is real. He concluded that the only thing he could be certain of was his own consciousness. I think, therefore I am. Everything else, including the physical world, could be an illusion. If the universe is a simulation, Descartes was onto something. If physical emptiness might be an illusion, a computational shortcut, but the experience of consciousness, the awareness of that emptiness, might be the only thing that's truly real. Here's a thought experiment. If you're a simulated consciousness in a simulated universe, are you real? I'd argue yes. Your thoughts are real to you. Your feelings are real to you. Your experience of the empty universe is real to you. The substrate doesn't matter. The experience is what counts. We've talked about the physical emptiness of the universe, but we haven't fully addressed the most mysterious thing of all, consciousness. How does subjective experience arise from objective emptiness? The hard problem of consciousness, as philosopher David Chalmers calls it, is explaining how physical processes in the brain give rise to subjective experience. Why does it feel like something to be you? Why aren't we just philosophical zombies beings that act conscious but have no inner experience? Here's where emptiness becomes relevant. Your consciousness exists in a physical brain that's mostly empty space. The neurons firing in your head are made of atoms that are 99.999999999999996% void. The electrical signals creating your thoughts are electrons moving through mostly empty space. Your subjective experience, the redness of red, the painfulness of pain, the you-ness of you somehow emerges from patterns of emptiness. Some philosophers, like panpsychists, suggest that consciousness is a fundamental property of the universe, present even at the level of individual particles. In this view, electrons have some tiny amount of experience, and complex arrangements of particles create complex experiences. Your consciousness would be the integrated experience of trillions of tiny consciousnesses working together. But if consciousness is fundamental, then the emptiness of the universe is filled with potential consciousness. Every particle, every quantum field, every point in space might have some infinitesimal glimmer of awareness. The void isn't empty, it's dimly aware of itself. Other theories, like integrated information theory proposed by Giulio Tononi, suggest that consciousness arises from integrated information processing. Systems that integrate information in specific ways generate consciousness. Your brain is a massively integrated information processor, so it generates rich conscious experience. But here's the kicker. If consciousness is about integrated information, then the emptiness of the universe might be necessary for consciousness to exist. If space were packed full of matter, information couldn't flow. There would be no change, no processing, no integration. The void allows information to move, change, and integrate. Emptiness enables consciousness. The quantum measurement problem adds another layer to this. In the Copenhagen interpretation of quantum mechanics, measurement causes wave function collapse. But what counts is a measurement. Is it any physical interaction, or does it require a conscious observer? John von Neumann and Eugene Wigner suggested that consciousness might play a special role in quantum mechanics, actually causing wave function collapse. If this is true, it's controversial. Then consciousness doesn't just observe the universe, it creates it. The emptiness exists in superposition until consciousness measures it and makes it real. Roger Penrose and Stuart Hameroff have proposed that quantum processes in brain microtubules might be the source of consciousness. If they're right, then your consciousness is directly linked to quantum phenomena, to the same weird, probabilistic, observation-dependent reality that governs the behavior of particles in the emptiness of space. There's also the question of whether consciousness can exist without a physical substrate. Could consciousness be uploaded to a computer? Could it exist as a pattern of information in some medium other than biological neurons? If so, then consciousness might be independent of the particular emptiness, atoms in your brain, it currently inhabits. It might be a pattern that can be instantiated in different substrates. But even if consciousness can be uploaded or transferred, it would still be a pattern in some physical system. And that system would still be mostly empty space if it's made of atoms, or mostly empty bits if it's made of computational memory. There's no escaping the void. Here's something profound. Your consciousness is reading these words right now. Information is flowing from my consciousness, which encoded these ideas, through physical media, emptiness arranged in patterns, to your consciousness. Mind separated by space and time, communicating through carefully arranged void. That's what language is. That's what writing is. It's consciousness reaching through emptiness to touch other consciousness. We've covered the physics, the mathematics, the philosophy. Now let's address the elephant in the room, or rather the vast, empty room with no elephant. What does all this emptiness mean for meaning itself? If we're mostly empty space in a mostly empty universe that's mostly headed toward maximum emptiness, does anything matter? Is there meaning in the void? Or are we just creating comforting illusions to distract ourselves from the fundamental emptiness of existence? Albert Camus, in The Myth of Sisyphus, argued that life is absurd. We're meaning-seeking beings in a meaningless universe. We're constantly trying to find purpose, significance, patterns, while the universe just is, indifferent to our desires. The emptiness of the universe reflects this absurdity. But Camus didn't conclude that we should despair. Instead, he suggested we should embrace the absurd, create our own meaning, and find happiness in the struggle itself. Like Sisyphus pushing his boulder up the mountain, only to watch it roll down, we can find fulfillment in the doing, not in some final achievement or external validation. The emptiness of the universe, from this perspective, is liberating. There's no cosmic purpose we're failing to fulfill. There's no grand plan we're disrupting. We're free to create our own meaning, our own purposes, our own values. Viktor Frankl, a psychiatrist who survived Nazi concentration camps, wrote about the importance of finding meaning, even in the most horrific circumstances. His message: meaning isn't given to us by the universe. We create it through our choices, our relationships, our actions. The void doesn't provide meaning, but it provides a canvas. The emptiness is neutral, it's neither good nor bad. It's what we do in that emptiness, how we connect across it, what we build in the midst of it that creates meaning. Think about love. When you love someone, you're creating a connection across the void. You're two mostly empty beings, recognizing each other, choosing each other, creating something real and meaningful in the emptiness. That love doesn't exist in the atoms. It exists in the pattern, the relationship, the shared experience. It's emergent from emptiness, but not reducible to it. The same is true for art, music, literature, science, philosophy, all human endeavors. We're creating patterns in the void, arranging emptiness in meaningful ways, leaving traces of our consciousness for other consciousnesses to discover. The heat death of the universe, the eventual fade out into maximum entropy, doesn't negate the meaning of what happens between now and then. The fact that your sandcastle will be washed away by the tide doesn't mean building it was meaningless. The experience of building it, the joy of creation, the beauty of the temporary structure, these are real, even if they don't last forever. In fact, the temporary nature of everything might make it more meaningful, not less. If everything lasted forever, nothing would be special. It's the scarcity, the fragility, the ephemeral nature of order and complexity in a mostly empty, entropy-driven universe that makes them precious. Bertrand Russell wrote, "Brief and powerless is man's life. On him and all his race the slow, sure doom falls pitiless and dark." It sounds bleak. But he continued, suggesting that in recognizing our cosmic insignificance, we can find freedom from petty concerns and focus on what truly matters to us. The universe's emptiness puts our problems in perspective. That argument you had, that embarrassing moment, that failure, they're infinitesimal fluctuations in a vast, indifferent cosmos. But that same perspective makes our connections, our kindnesses, our moments of joy and beauty infinitely precious. We're creating flickers of meaning in an overwhelmingly empty and indifferent universe, and that's remarkable. Let's pull everything together. We've journeyed from atoms to the edge of the observable universe, from quantum fields to cosmic voids, from physical emptiness to existential questions. What have we learned? The universe is empty. Profoundly, overwhelmingly, incomprehensibly empty. Atoms are mostly void. Space between planets is mostly void. Space between stars is mostly void. Space between galaxies is mostly void. The universe is expanding, making the voids larger. Dark energy is accelerating that expansion. Everything is trending toward maximum emptiness. And yet, in the midst of this emptiness, complexity exists. Stars fuse hydrogen into helium, creating heavier elements. Planets form. Life emerges. Consciousness arises. Meaning is created. The paradox is this: the emptiness is necessary for the complexity. If space were full, nothing could move, change, or evolve. The void allows for possibility, for motion, for becoming. Emptiness is not the absence of something, it's the potential for anything. You are a pattern in the void. Your atoms are mostly empty. Your body is mostly empty. The space around you is mostly empty. And yet, you are more than the sum of your parts. You are conscious, aware, capable of understanding your own emptiness. You are the universe observing itself, understanding itself, creating meaning for itself. Every scientist we've mentioned, Rutherford discovering atomic emptiness, Shapley measuring cosmic distances, Hubble discovering expansion, Penzias and Wilson finding the cosmic microwave background, Perlmutter, Schmidt, and Reese discovering dark energy. They were patterns in the void trying to understand the void. And they succeeded, at least partially. The fact that we can understand the universe's emptiness is itself profound. We're made of the universe, and we can comprehend the universe. We're not separate from the emptiness. We're part of it. Temporary local decreases in entropy, islands of complexity in a sea of void. Think of it like this. The universe is a vast, mostly empty ocean. Galaxies are like islands, but even these islands are mostly empty. Just look at the space between stars. You're like a wave on that ocean, a temporary pattern in the water, existing for a brief moment before dissolving back into the sea. But while you exist, you can observe the ocean, understand the ocean, and even appreciate the ocean. The ancient Buddhist concept of dependent origination suggests that everything exists in relation to everything else. Nothing has inherent, independent existence. You exist because of the sun, which provides energy, the earth, which provides a place to exist, your parents, who provided genetic information, the food you eat, which provides matter and energy, the air you breathe, which provides oxygen, and countless other factors. You're a nexus of relationships, not a standalone thing. And all those relationships exist across emptiness. The sun's energy travels through 93 million miles of vacuum to reach you. The atoms in your food traveled through interstellar space for billions of years before ending up on Earth. You're connected to everything through the void. Martin Heidegger wrote about thrownness, the fact that we're thrown into existence without choosing it in circumstances we didn't create. We're thrown into this mostly empty universe, on this mostly empty planet, in these mostly empty bodies. But our response to that thrownness is what defines us. We can despair at the emptiness, or we can marvel at the improbability of our existence in the midst of it. We can feel insignificant against the vast cosmic void, or we can feel special as conscious beings capable of contemplating that void. The choice is ours. The universe doesn't care. The emptiness is neutral, but we can choose to create meaning, to connect across the void, to build something beautiful in the midst of nothing. Here's the final mind-blowing thought. Every atom in your body was once in a star. Those atoms were forged in nuclear fusion, scattered by supernova, drifted through interstellar emptiness, condensed into new clouds, formed our solar system, ended up on Earth, and eventually became you. You are literally made of stars, arranged in a temporary pattern, capable of contemplating the journey those atoms took through billions of years of cosmic emptiness to become you. And someday, those atoms will disperse again. You'll dissolve back into the void. Your atoms will join the cosmic recycling program, potentially becoming part of future stars, planets, maybe even other conscious beings. But right now, in this moment, those atoms are arranged as you. They're thinking these thoughts. They're feeling these feelings. They're aware of their own emptiness and their own existence. That's not meaningless. That's miraculous. We've reached the end of our journey through the emptiness of the universe. But really, this is just the beginning. Now that you understand how empty everything really is, you can never quite see the world the same way again. When you touch something, you'll remember that you're not really touching it, just getting close enough for electron clouds to repel each other. When you look at the night sky, you'll remember that the space between those stars is so vast that light takes years to cross it. When you think about your place in the universe, you'll remember that you're a temporary pattern of mostly empty atoms in a mostly empty cosmos. But here's what I want you to take away from this. The emptiness doesn't diminish you. It illuminates you. The fact that you exist at all, in the midst of such overwhelming void, is statistically absurd and philosophically profound. You are not separate from the universe. You are the universe experiencing itself. You are emptiness arranged in a specific way, aware of its own emptiness. And in that awareness, in that consciousness, meaning emerges from meaninglessness, significance emerges from insignificance, and something emerges from nothing. The universe is empty, yes, but it's also full of potential, full of possibility, full of wonder. And you are part of that fullness, even as you're made of emptiness. So what do you do with this knowledge? You live, you love, you create, you connect. You reach across the void to touch other consciousnesses. You build meaning in the midst of meaninglessness. You appreciate the improbability of your existence. You marvel at the fact that you're here at all. The universe is mostly empty, but your life doesn't have to be. Fill it with experiences, relationships, growth, joy, wonder, and purpose. Not because the universe demands it, but because you choose it. Remember, every person you meet is also a pattern of emptiness. Every star you see is an island of fusion in a void. Every breath you take is pulling atoms from the air that were once in stars and planets and other living beings. You're connected to everything through the emptiness. Before we end, I want to hear from you. In the comments, tell me, how has this changed your perspective? What part of this blew your mind the most? And most importantly, what will you do differently now that you understand how empty and how precious everything really is? If you've made it this far, thank you for taking this journey through the void with me. Hit that like button if your mind was blown. Subscribe if you want more content that challenges your understanding of reality. Share this with someone who needs a cosmic perspective on their problems. And remember, you are mostly empty space, but you're also mostly miraculous. Never forget that.